All right, 2.2 is about organizing quantitative data. In 2.1, we talked about organizing qualitative data, and the steps that we take to organize quantitative data are very similar. There is sort of an additional layer of difficulty here, though, because our categories, instead of being labels like, location of injury or something like that, instead of being labels, the categories are going to be numbers themselves. And it's really easy to get the categories confused with the counts because it's all numerical, right? And then there are some other difficult things about organizing quantitative data as well. I mean, it's not difficult; it's just something that takes some getting used to. Okay, so we'll talk about these things as we move forward. One thing that we do with quantitative data is we'll construct what are called histograms instead of bar graphs. And really, histograms are the same thing as bar graphs, except for that histograms do not have gaps between the bars. There are no spaces between the bars like there are in a bar graph. And there are mathematical reasons for that that I'll point out to you as we draw some histograms, okay? So let's just practice. So this first one says the following data represent the number of available cars in a household based on a random sample of 50 households. Part A asks if the variable is discrete or continuous. So kind of a blast from the past, I guess, right? Testing our memory here. But is this discrete or continuous? Well, remember, discrete means that discrete is when you count up the value. Continuous is something, a continuous variable is one that you get by measuring, right? So the question is, did we measure these numbers or did we count these numbers, right? When we went to figure out the number of available cars, did we count that or did we measure that? And obviously we counted, right? So this would be discrete. This would be discrete data. Now part B says construct a frequency and relative frequency distribution for the data. Okay. So, so our frequency distribution would look like this. We're going to have a column for the number of cars, and then we're going to have a column for the frequency. Or in other words, the number of households. Okay. So number of cars. Now, if I look at my chart, there were some households that didn't have any cars available to them. So the smallest the number of cars could be is 0. And then there was one household that had 6 cars available to it. And I think that's the largest number of cars available. So I'm going to say number of cars, 0, 1, 2, 3, 4, 5, and 6. Right? So those are the possible number of cars available. Now the frequency, so we're looking for the number of households that have this number of cars. In other words, how many households had 0 cars? Okay, so if we go back and we count these up, we have 1, 2, 3, 4, I think 4. So I think there were 4 households with 0 cars in them, right? See, now this is what I was saying earlier when I said it's easy to get the categories mixed up with the frequencies, right? Because everything is numerical now. So try to keep this straight in your mind. This column represents the number of cars available. This column represents the number of households that has that number of cars. So there were 4 households with 0 cars available to them. There were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cars that had 13 households that had 1 car available to them, right? And so forth. So I'll let you finish this up, finish counting these up. So I think 22 households had 2 cars. I think 7 households had 3 cars. 3 households had 4 cars. I don't think there were any households with 5 cars. And then I think there was 1 household with 6 cars. And now to check my work, I can add these up and I hope that I get 50. Because if I don't, then I missed 1 or 2. So let's see, 4 plus 13 plus 22 plus 7 plus 3 plus 1 is 50. Yep, 50. So sure enough, I got it. Okay. So this would be our frequency distribution. Now, if we wanted a relative frequency distribution, then we would divide all of our frequencies by the total. So we would divide 4 by 50, and that would give us 0.08. In other words, 8% of households. We would divide 13 by 50, and that would give us 26% of households, right? And so forth. Here we would get 44%, 14%, 6%, 0%, and 2%. Okay? So, so 26% of households had 1 car available to them, and 14% of households had 3 cars available to them, and so forth. Somebody just came to my front door, and now my dogs are going to bark. Sorry about that. Okay, but that's that. That's our frequency and relative frequency distributions. Now, now we can draw a relative frequency histogram using those distributions as follows. So so on my x-axis, right, so on the horizontal axis, that's where I'm going to put the number of cars. And on my vertical axis, that's where I'm going to put the number of households, okay? And actually, I think I'm just going to draw a frequency histogram, not a relative frequency histogram, because I've already done a relative frequency histogram in the previous section, or a relative frequency bar chart anyway. So I'm just going to use the frequencies, right? Looking at the frequencies, the largest frequency is 22. So I need to scale my vertical axis so that I can get all the way up to 22 at least. So I think I'm going to do that by starting at 0 and going all the way up to 25 in increments of 5. So 5, 10, 15, 20. Oh, I could have done better than that, huh? And I used pen. Well, okay. Maybe I can go in 2s. 2, 4, 6, 8. No, that's too spread apart. Well, maybe if I split it like this. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. And that's good enough, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So this is the number of households. And down here we'll have the number of cars. So we have to go all the way from 0 to 6. Now, where the y-axis crosses the x-axis, that should be 0. So I'm not going to make a little tally mark and say 0 over here. That wouldn't make any sense, right? So this needs to represent 0. So if I put a mark here, then it's going to represent 1, 2, 3, 4, 5, and 6. So this is going to be the number of cars. And then as far as titles for this thing go, we can call this cars per household. Okay. All right, so when I draw my histogram, the way that I draw the bars is the number on the left, the bar represents the number of, is going to represent the number of households that have the number of cars on the left-hand side of the bar. In other words, there were 4 households with 0 cars, right? So there were four households with 0 cars. So I'm going to draw a bar at 4 that goes from 0 to 1. And that might seem a little bit strange at first, but again, you'll see why as we look at some more examples. But basically, this bar represents all of the households that had somewhere between 0 and 1 cars, not including 1. Okay, so in this case, since this is a discrete variable, it would just be the number of households that had 0 cars, right? There were 13 households with 1 car, so I'm going to draw a bar going up to 13, going from 1 to 2. So again, this represents all the households with somewhere between 1 and 2 cars, not including 2. So in other words, it's the number of households with 2 cars. Okay. The next one should go up to 22. Right, there are 22 households with 2 cars. And you'll notice I'm not putting gaps between these. 7 households with 3 cars. 3 households with 4 cars. 0 households with 5 cars. So there's going to be a gap here, right? Because there are 0 households with 5 cars. And then 1 household had 6 cars in it. So I'm going to have a little bar there. And that's that, right? So that would be the number of cars per. Kind of looks like it's flipping us off, right? But this would be a histogram for the number of cars per household, a frequency histogram for that. Okay. So that's the idea there. Okay, so no gaps between the bars, and the way that we label the x-axis is a little different, right? Again, we'll see why we label it this way. Okay, so in this example that we just saw, the variable was discrete. If we have continuous data, then it's unlikely that we would see the same measurement repeated. In other words, like here we had 22 people that had the same number of cars, right? In this case, 2, right? We had 22 households that had 2 cars in them. But if you were measuring someone's height, for example, like it would be really rare to come across 2 people that have exactly the same height. And so if you have a continuous variable, then you're not going to get a nice picture like this when you build the histogram unless you group the data into intervals, right? So you group the data into classes. So instead of making a different bar for every single height, you would maybe make a bar that goes from people who are 5'0" to 5'4", and then another bar for people who are 5'4" to 5'8", and then another bar for people who are between 5'8" and 6 feet tall, right, and so forth. And so we split the data up into classes. So if the data is continuous, or if the data is discrete, but there's just a lot of different kinds of observations, then we would split the data into classes. Okay, so let's fill this in though. The smallest value within a class is called the lower class limit. And the largest value within a class is called the upper class limit. And now this is incredibly important. This will mess you up if you don't pay attention to what I'm about to say, okay? The class width is the difference between consecutive lower class limits. Okay, the class width is the difference between consecutive lower class limits. It's very natural to think that the class width should be the difference between the upper class limit and the lower class limit, but that's not the case, okay? The class width is the difference between consecutive lower class limits. And again, I'll show you an example of this. You don't have to worry about this part. We'll skip that. These are guidelines for determining classes, and definitely in the real world, you would want to play with these a little bit to get classes that give you a nice looking picture. We'll do this in StatCrunch though, instead of trying to figure it out by hand. For the most part, on the homework and on tests and quizzes and stuff, I'm just going to tell you how many classes I want, what I want the class width to be, and where I want you to start and all that stuff. So you won't have to worry about figuring that out on your own. But let's look at another example. This says, consider the following data set of the length in centimeters of 40 fish from Black Lake. Is the variable discrete or continuous? Well, this is continuous data. It's continuous because they got these values by measuring, right? And in this case, they measured to the nearest centimeter, but they could have measured to any desired level of accuracy, right? So, so theoretically, right, they could have gotten as accurate as they wanted to, but anyway, they got the data by measuring, and so it's continuous data. Now, part B says, construct a frequency distribution and draw a frequency histogram for the data. Use a class width of 5 and a lower class limit of 20 for the first class. Okay, so frequency distribution. Okay, so we have the length of the fish and then the frequency with which that length was observed. So in other words, the number of fish. Right? Okay, so these lengths, and as you can see, there are a whole bunch of different lengths, and probably they don't repeat very often, right? You might have like a couple observations of like 42 or something, but then you're only going to have probably one observation of 52, and you're not going. Well, that's not true. I see another one down here, but the point is, right? You're not going to get, if you try to construct a histogram where each observation got its own bar, you would just get this really like flat distribution that wouldn't be it wouldn't illustrate anything. So instead, we're going to use classes. And actually, we're told, use a class width of 5 and a lower class limit of 20 for the first class. So when I say use a lower class limit of 20 for the first class, I'm giving you the starting point. I'm saying start at 20 and then have a class width of 5. Now, here's where people mess up, right? So don't write this down. You can just watch for a second. Right? But a lot of times people say, oh, the class width is 5. So that means the first class needs to go from 20 to 25. And now the problem with that is that they think, well, if I went from 20 to 25 in the first class, then the next class needs to start at 26. Right? And you run into a problem because the class width is not the difference between the upper and lower class limit. The class width is the difference between consecutive lower class limits. So what you've done here is you've created a class width of 6, not a class width of 5, right? We were asked to use a class width of 5. Okay? So if you want your class width to be 5, then really the next class needs to start at 25. And if the next class starts at 25, then the first class needs to stop at 24. Okay. Or if you like, you can say, well, it can go all the way up to 24.9 or 24.99999 or whatever. But the next class has to start at 25. Okay. And with that same thing in mind, right, the class after that would have to start at 30, and then 35, and then 40. So I think the best thing to do to not confuse yourself would be to fill in all of your lower class limits first, and then come back in and fill in your upper class limits. That's probably the most surefire way to not confuse yourself. So I'm going to fill in the lower class limits, 20, 25, 30, 35, 40. Now, how far should I go? I see 61, 62. Is there anything bigger than 62? I don't think so. So I'm going to go to 60, 40, 45, 50, 55, 60. And then if I need to fill in more, I will. But so this first class is going to start at 20 and end at 24, we'll say 24.9, right? And the next one needs to stop at 29.9. And the next one needs to stop at 34.9 and so forth. And then we can go back to the data and start to count up how many fish were between 20 and 24.9 centimeters, right? So let's look for those guys. There's one. Just one. Okay, 25 to 29. 3, 4. Okay, and so forth. So I'll let you work on the rest of these. And I need to add one more class because I noticed a 68 in there. And I think that takes care of all 40. Let me check my work real quick. Yep, that's all of them. Okay, so there's my frequency distribution. Now it says to draw a frequency histogram. So I'm actually going to tip my page over on the side so I have a little bit more room to do this. So my frequency histogram. So I need to go up to 7 on my y-axis. And then on my x-axis, I need to go all the way up to 70, but my class width is 5. So when I put my classes on here, I'm only going to put the lower class limits. I'm not going to label the upper class limits. I'm only going to label the lower class limits. So I need to go from 25 to 65. So what I'm going to do is I'm going to put a little symbol in here to tell my reader I'm not starting right at 0. And then I'm going to put 20, 25, 30, 35, 40, 45, 50, 55, 60, 65. Okay, so down here we have the length in centimeters. And then here we're going to have the number of fish. So I'm going to say 1, 2, 3, 4, 5, 6, 7. This is number of fish. Or you could just label it frequency if you like. Okay, number of fish. And then I'm going to call this graph length of fish in Black Lake. Okay. And so now I can go ahead and fill in my bars. So between 20 and 24.9, we had 1 fish. That was that length. Between 25 and 29.9, we had 4 fish. And now you get a better sense for why we draw histograms the way that we do. We don't leave gaps because this bar needs to represent all of the fish between 20 and 25 centimeters, not including 25 centimeters. And this bar needs to represent all of the fish between 25 and 30 centimeters, not including 30 centimeters, right? And so forth. So we don't leave gaps between the bars for that reason. Okay, 30 and 34. So there were 5. And then 6, and then 7, and then a couple of 5s, and then a couple of 3s, and then a 1. Okay, and there's our histogram for the length of fish in Black Lake. Okay. So that's it. Once you have a histogram, now we can talk about the shape of a distribution. And this is something that we can do for quantitative data that we don't really do for qualitative data. The reason we don't talk about the shape of a distribution when you're dealing with qualitative data is because since the data is qualitative, the categories that go along the x-axis can be arranged in any order you want. And so and when you rearrange stuff, the shape of the distribution changes. So it doesn't make sense to talk about the shape of a distribution when you're dealing with qualitative data. But when you're dealing with quantitative data like this, the x-axis labels have to be in order from 0 to whatever. And so consequently, you can't rearrange these bars however you want. And so the shape is a fixed feature of the distribution. And the shape of the distribution is going to be something very important to us later on in this course. So anyway, some of the main shapes that come up are these 4 things. There are other kinds of shapes, right? You could have bimodal shapes and all kinds of stuff, but these are the main ones, right? So a uniform distribution is one with a basically flat line going all the way across. A bell-shaped distribution looks like this, right? So if because you can it kind of looks like a bell a little bit if you follow the shape of the distribution. These 2 distributions are called skewed distribution. This one is skewed right and this one is skewed left. And at first glance, that may seem a little bit counterintuitive because you're thinking, well, most of the data over here is on the left-hand side of the graph, so why is it called skewed right? Well, the reason it's called skewed right is because, yeah, most of the data is over here on the left. So if you're talking about like a typical observation here, you would expect it to be on the left-hand side, and yet you have these values. You just have a few values over here that are really, really large compared to the rest of the data that end up skewing to the right, like the averages and stuff. So these values out here are sort of throwing off the average. They're pulling the average to the right. Okay, so it's a skewed right distribution. And the same thing here, right? So so this is a skewed left distribution because you have these values over here to the left that are sort of pulling you down. What it looks like, another way to see this is, what it looks like is that you started with a bell-shaped distribution, but then if you're skewed right, it looks like you just took the right-hand side of this and you stretched it out, right? You stretched it out to the right. And so you got a skewed right distribution. Or if you stretch out your symmetric distribution to the left, then you get a skewed left distribution. Okay, so that's where those names come from. With that in mind, it says, what is the shape of the distribution in example 1? So going back to example 1, that was this cars per household business. I would say skewed right. Okay, I would say skewed right. What's the shape of the distribution in example 2? That was this length of fish in Black Lake. That looks pretty much symmetric to me. I would call this a symmetric, a bell-shaped distribution. Okay. There is a little bit of subjectivity here, right? So it's a little bit subjective. you know, what shape you say these distributions have. In the future, we'll have a more mathematically rigorous way to determine if something is bell-shaped, because that's going to be really important for us to determine if something has a bell-shaped distribution. Okay, so histograms, bar charts, and frequency distributions are really our main tool for organizing data. However, there are other kinds of charts. I'm sure you know about like pie charts, and there are stem and leaf plots that we actually will talk about in chapter 3. And there are lots of others, right? So there are like frequency polygons and like all kinds of stuff, right? So we could talk about all kinds of different types of graphs, but those are the most important ones. One type of graph that I do want to talk about are stem and leaf plots, because stem and leaf plots I think are a little bit hard to read if you don't know where they come from. Like a pie graph, I think anybody could read a pie chart, right? It's pretty straightforward. But a stem and leaf plot is like what does this even mean? Unless you've seen it before. And so, so I'd like to expose you to that now. So with a stem and leaf plot is a chart used to organize data from smallest to largest. The rightmost digit is the leaf, and the rest of the digits form the stem. So for example, if you had a data value of 147, then 7 would be the leaf, and 14 would be the stem. Okay, so the leaf is always just one digit. It's always the digit on the right. Okay. So let me just give you an example, creating a stem and leaf plot. So here we have 20 data values. And let's make a stem and leaf plot out of this. These values represent the number of miles that students live from COS. So apparently all of these students live in town. Nobody's coming from Wood Lake or something like that. But anyway, let's make a stem and leaf plot. So the first thing I'm going to do is I'm going to make all of my stems. And it looks like the smallest stem is 0, and the largest stem it looks like is 4. Okay, so I'm going to make my stems 0, 1, 2, 3, 4, and then I'm going to draw a vertical bar. And then I'm going to start to put leaves on each of these stems. Okay. By the way, this first one that I do is just a rough draft. Okay. But so going through now 3.4, that means that I should have a leaf of 4 on my stem of 3. And then 3.2 means that I need to have a leaf of 2. And 3.8 means that I need to have a leaf of 8. And you don't need to put a comma between each of these numbers or anything like that, because as we said on the previous page, leaves are always just a single digit. So you know that each one of these numbers represents a different observation, right? This number represents an observation of 3.4. This one represents an observation of 3.2, right? And so forth. 0.8 would go up there, 4.5 would go down there, and so forth. 1.2, 2.3, whoop, 2.3, sorry, this one should be 3.5. 0.2, 3.2, 2.8, 2.5, 1.6, 2.4, 1.9, 4.3, 2.7, 2.6, 2.8, 2.6. Okay, so there's my first draft for a stem and leaf plot. My final draft needs to put the leaves in order from smallest to largest. So I'm going to redraw this now. 0, 1, 2, 3, 4. And I'm just going to rearrange my leaves so that they're in order. 2, 8. Oh, this one's already in order. 2, 6, 9. This one, I need 3, 4, 5, a couple 6s, a 7, and then a couple 8s. Okay. And this one I have 2, 2, 4, 5, and 8. And this one I have 3 and 5. Okay, and then the other thing that you need to do is you need to give your reader a key so that they know what this is, right? Because if somebody didn't have the raw data and they were just going off of this stem and leaf plot, they wouldn't know if 0 bar 2 means 2, or if it means 0.2, or if it means 20. They wouldn't know, right? So you have to tell them. You have to tell them that in this case, whenever you see, for example, whenever you see 2 bar 3, that means 2.3, right? It doesn't mean 23, it doesn't mean 230, it doesn't mean 0.23, it means 2.3, right? And that's the only way your reader's gonna know that, is if you have that key. But that's that. Stem and leaf plots are really nice because, well, it gives you a way to organize your data without losing any of the raw data, okay? Like if you compare this to a histogram, with the histogram, sure, you get these nice looking graphs and stuff, and you have some idea, right? It's like you know that there were 4 fish that were somewhere between 25 and 30 centimeters, but you don't know what the exact measurements were, right? You lose that information. Whereas in a stem and leaf plot, you retain all of the information still, and hey, by the way, you turn it over on its side and you get a histogram for free, right? So they're really pretty nice graphs. So then you can talk about the shape of the distribution and stuff. But anyway, that's that. I'm not going to complete number 5, but I do just want to get started on it to show you, just to make it perfectly clear about stems and leaves and all that. So here where we have 3-digit numbers, remember the leaf is still only the last digit, okay? And everything else is the stem. So if I were wanting to make a stem and leaf plot, I think I would probably start at like 67 and go up to 73 or something. So 67, 68, 69, 70, 71, 72, 73. And then I would put a vertical bar, and then I would start to put my leaves on there. So for 728, I would put a leaf there. For 730, 726, 698, 721, 722, 700, right? 720, 729, right? 678, and so forth, right? So again, it's only the rightmost digits. And in this case now, when you're with your key, you'd have to point out that, you know, something like 69 bar 8 means 698. It doesn't mean, right? It doesn't mean 69.8 or 6.98 or 0.698 or whatever, right? It means 698. You have to give them this key so that they know that. Okay. So that's that. I'm not going to, like I said, I'm not going to complete this example, but that's how stem and leaf plots work. Now, the last thing that I want to talk about is how to make graphs and charts in StatCrunch. So I'm not going to, here are some directions on how to do some of these things. I'm just going to take you to StatCrunch and play around a little bit. I took the liberty of putting in some values into StatCrunch already, so that I wouldn't have to sit here and enter the data. But of course, in order for you to be able to do something in StatCrunch, you need to enter the data first, right? So you need to take some time to enter all of this data in. Oh, and I think I messed up here. Let me see. This was supposed to be the length of fish in Black Lake. So I think instead of 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it should have been 57. I just noticed that. Anyway, so we can do a whole bunch of stuff, right? Like, let's say that we wanted to make a bar graph out of the location of the injury, right? To make a bar graph, you go to graph and then bar plot, and then either with data or with summary. Now in this case, if I'm wanting to make a bar graph out of this information, this is the raw data. It's not a summary of the data. It's just the raw data itself. So I would say graph, bar plot with data. And then I'm going to say injury location, and then hit compute, right? And so then it gives me a nice bar chart. If I wanted to make a bar chart out of this information, on the other hand, like if I wanted some kind of side-by-side bar chart out of this information, like let's say I wanted a bar chart for the US residents by race, okay? So this time I have a summary of the data. This is not the raw data, it's a summary. So I would go to graph bar plot with summary. And then I would say, well, the categories are in the race column. And the frequencies, the counts are in the, if I wanted to make a one for the US, it would be in the US column. Okay, and then it gives me that information. Okay, if I wanted a side-by-side bar graph, well, then I have to do something a little different. I go to graph and then chart and then columns. Let me see if I remember how to do this. It says select columns. So if I want to make a side-by-side bar graph for the US and California, I would select both of those. You can do that by just clicking and dragging, or you can do it by holding down Control on your keyboard and clicking on both of those things. And then row labels, I'm going to say race. And I want to draw my bars vertically. So hit compute. And then it gives you that side-by-side bar graph that we came up with in class. Actually, this is not the side-by-side bar graph that we came up with in class, because what we did were relative frequencies, and this is a frequency bar graph. So if we wanted a relative frequency bar graph, then I'm going to do the same thing, but with the relative frequencies. There you go. That's the bar graph that we drew back in 2.1 together. Okay, so that's that. Oh, going back to the location of injury thing. So if I want a bar graph for that, again, I have the raw data, so I'm going to say with data. But I can choose to make this, I can choose to either do a frequency bar graph or a relative frequency bar graph instead. Okay, now I've got the relative frequencies instead of the frequencies. Anyway, so that's how you do stuff with qualitative data. Oh, another thing I could do with the location of injury is I could make a frequency distribution. To make a frequency distribution, since it's not a graph, it's a chart, you're going to go to Stat, Tables, Frequency, and then Injury Location. And I can make a frequency or a relative frequency or both, right? I could go ahead and do both. And then it gives me that frequency distribution that we came up with together, right? Which is really nice. Okay, so that's qualitative data stuff. For quantitative data, right, that's this stuff that we just did in 2.2. I can do similar things, right? Like if I wanted to make a histogram out of the number of fish in Black Lake or something, I could go to graph, histogram, and then I'm going to select the fish column, and I'll just do a frequency histogram. So we do a frequency histogram, and then you hit compute, and it gives us the histogram that we drew together. Now what you'll notice is that when it does this histogram, it automatically makes the class width 5, and it automatically makes the class start at 20, which matches what we did together in class. But if you didn't want that, if you wanted a different class width, then what you could do is you could go back to where you started, and here where it says bins, start at, and width, instead of having a class width of 5, right? So if I say start at 20 and have a class width of 5, that's just going to be the histogram that it just drew, right? That's that histogram that it just drew. But if instead of a class width of 5, I wanted a class width of, I don't know, like 3, then I could make StatCrunch do that, right? I could just change the class width to 3. It doesn't give me a very nice looking picture, right? But I could do it. Or I could make it bigger and make the class width 8 or something like that, right? So you can play around with the class widths a little bit to get a nice looking picture. And StatCrunch makes it really easy to do that. If I wanted to get a frequency distribution or a relative frequency distribution out of continuous data like this, then there are a couple ways to do it. I'll give you two ways, a hard way and an easy way. The hard way to do it would be to, first you would have to bin this data, right? So you'd have to go to something like data bin, and then say, I want to bin the fish data, and then I want to bin it into groups of 5, starting at 20 and having a bin width of 5. And then you hit compute, and it spits out this new column that has the data binned into these different classes, right? And now I can go to stat tables frequency and create a frequency distribution for the binned data. See, then I get the frequencies and relative frequencies for the binned data. If I just do that with the raw data the way that it was in this column over here, I'm not going to get the correct results. Fish, right? And compute. See, you get this error that says, whoa, lots of unique numeric values for fish. Want to turn on binning for this procedure? And, you know, you can say okay, but there's no guarantee that it's going to give you the same bins that you asked for. Like in this case, it's binning by 10s instead of binning by 5s, like we wanted it to do. So, so that gives you kind of bad results, I guess you could say. So you have to bin the data first before you can create the frequency distribution. Whenever you have qualitative data, you have to bin it first by going to data and then bin. So you have to bin it first, and then you can create the frequency distribution. That's the hard way to do it, though. The easy way to do it would be to just make a histogram, right? Just make a histogram, say graph, histogram, fish. And then you have total control over the bin. And then if you wanted to know what the frequencies are, you could just click this little box that says value above bar, and then it gives you the numbers, right? So that's pretty nice. And if you hover over the bars, it tells you what the classes are, right? This first bar goes from 20 to 28, including the 20, but not including the 28. And that's why it has a square bracket on the 20 and a rounded parenthesis on the 28. That indicates that that class goes from 20 to 28, including 20, but not including 28. This one goes from 28 to 36, including the 28, but not including the 36, and so forth, right? So you could just make a frequency distribution using your histogram to do it. I think that's all I want to show you. Ultimately, like, you're going to become familiar with StatCrunch by getting in there and playing around with it. You can watch me do stuff all day. It's probably not going to be as helpful to you as you just getting in there and playing around a little bit. So there you go. That's all I have for 2.2.